Today, let us discuss about. Yesterday we are discussing about wing geometry selection, correct? So today, let us
Yes.
discuss about, and also yesterday we are learning about the wing tips and the winglets. What is the importance of the winglets and the wing tips? See here, winglets mainly what it is, the wetted area increases versus reduced drag. So these are called as a winglets. We'll call. You can see that at the end portion, we can see this is called winglets. We'll call it. It's called what? Winglets. Okay. Why this winglets is it? Because
Yes.
to reduce the induced drag. To reduce the induced drag means drag due to lift. Drag due to lift. Okay. So yes. So it's a drag due to lift. And we can look here, biplane wings. What are these biplane wing? Each wing contributes one half of the required lift. Induced drag reduces by factor of 2 factorial, that is 2 into 1. But parasite drag, that is called zero lift drag. What is this parasite drag? Is nothing but a what? CD naught. CD naught is nothing but a what? Zero lift drag will go up. Wing interference reduces
Sir,
manipulation.
sir,
Yeah, yeah.
screen sharing is not showing.
It's not showing.
Yes, sir.
1 minute. Now it is showing. Now it is showing.
No, sir.
Yeah.
No, sir.
Okay, okay.
No, sir.
It's not showing now.
No, sir.
Now, now it is showing.
Yes, sir.
Fine. Okay, fine. So now, so we look here. So biplane wings. Biplane wings means what? Each wing contributes one half of the required lift. Induced drag reduces by a factor of 2 factorial. So here, when you look here, CD naught. CD naught is nothing but a what? Zero lift drag. We will call it. It's called zero lift. This is the drag where the lift will be zero. That is called CD naught, or it maybe it's called as a parasite drag. We'll call it. It's called parasite drag. Wing interference reduces lift. We can see that we have a wing 1 and wing 2. We can see right hand wing as well as left hand wing. We'll call it as wing 1 and wing 2. So for example, the coefficient of lift 1, so L1, it is equal to CL2, that gives rise to CL by 2. So therefore CL by 2 plus CL by 2 will get a total lift of the both the wings. So therefore the equation is CD is equal to CD naught KCL square by 2. What is this? KCL is 1 pi E epsilon naught. We'll speak about Oswald efficiency and other things in the further things I will discuss about it. This is called KCL 1 square. KCL 2 square is nothing but a what? This is for wing 1 and this is for wing 2. Okay, so the biplanes are still worth considering if span is limited but wing area is needed for low speed flight, high roll rates are needed, and aerobatics. So what is this aerobatics? So aerobatics is nothing but a what? The aircrafts like mainly for maneuvering purpose, or it may be for a sports purpose. They are called as aerobatics. Aerobatics we will call. And mean aerodynamic chord for the airplane is defined by the weighted average of the aerodynamic chords of the each wing, weight set by area of each wing. So see, biplanes are still worth considering if span is limited but wing area is needed for low speed flight and high roll rates are needed, that is for aerobatics. And mean aerodynamic chord for airplanes is defined by weighted average of the aerodynamic chords of the each wing. It's a weight set by area of each wing. We can look here, tail geometry. We can see tail geometry. We have a tail functions. Tails are little wings already. When we are discussing about tails, we have horizontal as well as vertical. They're called stabilizers, we will call. So they're called where the vertical tail is consisting of a rudder and horizontal tail is consisting of an elevator. It have its own. They're called as a for stabilizers, and also they're called as a little wings, we will call. They're called as what? Little wings. And much of previous discussion concerning wings can also be applied to the tail surface. Yes, it's also applied to the tail surface. And the major difference between the wing and the tail is that, please we have to understand the difference between the wing and the tail is that while the wing is designed to routinely carry a substantial amount of lift, it is to carry a substantial amount of lift, a tail is designed to operate normally to only a fraction of lift potential. It is just for a, it is not, it is just for a small amount of lift. It is not a larger amount, a substantial amount of lift. The tail designed to operate normally at only a fraction of lift potential means it acts like a stabilizing. It's like it acts like a stabilizer. So any time in flight that a tail comes close to its maximum lift potential, hence its stall angle, means what it says we have to understand here. Once the tail comes to its maximum lift, it means that when it reaches at a higher angle of attack, where the maximum lift will be there, once that angle it crosses, then where the lift will reduce and the drag will be higher. Hence it's called as a stall angle, we will call. At that time the stability of the aircraft will not be there. So therefore you have to take consideration of the tail also. Something is very wrong, because if it is loses its control at that time, aircraft will not be in control. Sometimes it may go and crash. So therefore it is very important, the tail functionality in the stabilizing part of the aircraft. Okay, the tails provide for trim, stability and control. The trimming is the aircraft is nothing but a what? The trim is nothing but a the stabilizing the aircraft roll, pitch, and yeah, all the moments will be zero at that point. It's called trim point. We'll call it. It's called trim point. Trimming the means it's nothing but a what? Trimming the aircraft is nothing but a what? Where the pitch, roll, it will be equal to zero. Roll, pitch, roll, and yaw. All these three moments will be zero. Okay, and stability. Already we discussed about a stability. Whenever you disturb the any object, it will come back to its original position. Correct. So therefore, that stability, when the aircraft is stable, for example, when the wind comes, that's called a gust comes. When it goes disturbs, again it should come back to the original position. When it goes to the pitch up, again it should come back to the same normal condition. Otherwise, pitch up, pitch up, pitch up, pitch up. If it goes and it should not get crash. Correct. Pitch down. If action is there, it is going pitch down action and is not coming back to the stabilized position. Then also it may be create to the biggest that it goes something wrong. So therefore the stability of the aircraft is more important. And also control. The control is nothing but what aircraft should be controlled. And for example, with the control surfaces, it may be elevator will control the pitch, and rudder will control the yawing moment of the aircraft, and ailerons control the roll of the aircraft according to that. So trim refers to the generation of lift force that by acting through some of the other moments, arm above the center of gravity balances some other moment produces by the aircraft. We can look here for the horizontal tail. Trim primarily refers to the balancing of the moment created by the wing. And aft horizontal tail typically has a negative incidence angle. It's about 2 degree to 3 degree to the balance the wing pitching moment, because it should balance the wing pitching moment. So therefore it's having 2 to 3 degree. We can see here this is called vertical stabilizer, it is called horizontal stabilizer, this is called rudder, they're called the trim tabs, and these are called as elevators. For vertical tail, most of the aircraft are left right symmetric. In the vertical tail we have a left right symmetric. Left right, you can look here, there is a left right symmetric. And so unbalanced aerodynamic yawing moments requiring trim are not created during the normal flight. The major functions of tail is to control of the aircraft. It is to control the aircraft. Major functions of the aircraft, like you have to know about it. Major function of the tail is to control the aircraft. Clear? So, and propeller aircraft experience a yawing moment called P effect. Please, you have to know about it. In the propeller based aircrafts mainly, because the propeller will be there at the front, that yawing moment, it's called as a P effect. It's called a propeller effect. We will call it. It's called propeller effect, which has a several thrust related causes. Because we have a thrust related causes, there will be a lot of like force will be acting on the propeller. And so when the disc of the propeller is at an angle such as during climb, blade going downward as a higher angle of attack and is also slightly higher forward velocity, this condition produces a higher thrust on the downward wing, downward moving side, and say yawing movement away from that side. Also, the propeller tends to drag the air into the rotational corkscrew motion. It's called corkscrew motion. And uh, and the vertical tail is pushed on the sideways and rotating the prop wash, causing the yawing moment, which adds the P effect. To counter the P effect, many single engines propeller airplanes have the vertical tail offset several degrees. So therefore, to avoid this effect, because the yawing moment mainly the rudder, so will increase the size of the will increase the size of the height of the rudder, because by increasing, what happens, it will gives the directional stability of the aircraft. So therefore, the increasing the area or increasing the height of the increasing the height of that vertical tail, it will effect on the P effect in the main layer, and also it gives the directional stability for the aircraft. And vertical tails of multi-engine aircraft must be capable of providing sufficient trim in the event of engine failure, and this produces the yawing, both the lack of thrust on one side and extra drag of the stopped on the windmilling engine. So therefore, some multi-engine aircraft have counter-rotated propellers to minimize the engine out yawing. So therefore, to avoid it, because one side will be higher we have a more weight and other things will be the less, so it may leads to the imbalancing of the aircraft. To avoid that, so we have to take care these effects. And we have there also have a key parameters, a key element of stability, and much like the fins on arrow to restore the aircraft from the upset in pitch or yaw. If it goes pitch up, again it should come back to the same, again the stabilizing position. If it goes yaw towards left, again it should come back to the original position. This stability should be there. Otherwise, if it is going left and should going left, it should not go and it should not come back to its original position. Sometimes it may leads to the crash. So therefore, we have to the tails plays a very important role in the stability of the aircraft. We have to remember what is the functionality of the tail. Tail is the key element of stability, acting much like the fins on an arrow. Because why we can see that arrow, so whenever you bow and arrow, when you look into it, arrow, we have a feather like the structure will be there. You can see that inside backside of it. Why that will be there? To give the stability part of it. So the tail, what we are fixing for the arrow, it is mainly for the stability of the bow, for the arrow, to restore the aircraft. So in the same way, a tail also, why we are keeping up? To restore the aircraft, means from the upset of pitch or yaw. Okay. And action of the horizontal stabilizers is much more complex and involves a delicate balance of the pitching moment due to the location of the wing center of lift relative to the center of the gravity, the inherent pitching moment of the wing, the pitching moment generated by the horizontal stabilizer, and the way these moments change the wing angle of attack. Sometimes these horizontal stabilizers may change the with the angle of attack, so therefore it may leads to the adverse moments, for example adversia, proversia, and it may lead to the Dutch roll. Correct. So therefore these are all of the effect will be that we have to take into consideration. Because on the horizontal tail, we know that elevators will be fixed. The function of the elevator is the aircraft pitch up and pitch down, and also if it is change with the angle of attack, so therefore it will affect on the wings also. So we can see that tail arrangement, we have a different type of tail arrangement. We have to know about it. We can see here these are called as a conventional type of tail. You can see they're called this type of tail. Whenever you look the aircraft, by looking the aircraft, you have to tell what type of tail it is. So being a design engineer, so you have to know that by looking the aircraft, we can tell that okay, this is a twin engine, this is a twin engine aircraft, this is a swept back aircraft, this is having a conventional tail, this is having we have a tail dragger, such type of landing gear, we have otherwise bogie type of landing gear. So by looking itself, we have to tell what type of nose it is, what type of tail it is, what type of wing it is. Correct. So this is the design engineer should have a good eye. By that he can do the best the designs. So therefore we can see that this is called conventional tail, this is called T tail. We can see where the horizontal tail kept on the top of the and the vertical tail, and we can see this is called cruciform in midway of the now and midway of the vertical tail, and also we can see this is called H tail, and this is called triple tail, and this is called V tail, this is called inverted V, and this is called Y tail, correct? So these are all the different types of uh, uh, tails configuration. You can see this is called conventional type of aircraft. The most aircraft designs, the conventional tail we use will use to provide the adequate stability and control the at the lightest weight. It will be having a lightest weight, and also when you keep here the horizontal tail at that on the vertical tail, it may leads to the inherent heavier than a conventional tail, because the vertical tail must be strengthened to support the horizontal tail. That but the T tail provides the compensating advantages in many cases. So we can look here due to the end plate of the effect. You can see here, this is you can see that. So when the air is flowing over that, this is the airfoil, and you can see at the angle of degree, and we can see that is the flow over it, and we can see, and it's called turbulent zone. If it is turbulent zone where the wake formation will be higher, at the time we may lose uh, the control over the control surfaces. So therefore, by keeping of this, and we have a lot of effects, we can look into it, and we can see this, there will be a rudder wear, and we can see that when you keep this vertical tail when the horizontal tail over the vertical tail, there we can see the flow over it, and also the by deflecting of the elevator is also effect on the sometimes on the rudder effect also. So there have a lot of effects will be there. So therefore here they says that T tail allows a smaller vertical tail, and the T tail lifts the horizontal tail clear of the wing wake and prop wash, and which makes it more efficient, hence the allows the reducing its size. You can reduce the size, and also we can also, you can see here, this also reduces the buffet of the horizontal tail, and we can see this is called buffet of the horizontal tail. So we can see here, we can see that when it is pitch up moment, we can see here, and the flow over it, and this portion, mainly this portion. So you can see that deep stall is dangerous type of a stall that affects the certain aircraft designs, notably those with a T-tail configuration. In these designs, turbulent wake of the stalled main wing and blankets, and the horizontal stabilizer rendering the elevators ineffective and preventing the aircraft from recovering of the stall. So therefore, recovering of the stall, the boundaries of the acceptable locations for horizontal tail to avoid this problem is given of the figure. So low tails are best for the stall recovery. So therefore, low tails are best recovery for the. So by conclusions is what? So for if we have a low tails are the best stall recovery. A tail approximately in line with the wing is acceptable for subsonic aircraft, but may cause problems at supersonic speeds due to the wake of the wing. We can see here this is for quarter cord portion, and we have a tail arm, and we can see avoid the tail gets blanketed. So according to that wing quarter cord, according to subsonic only, and with a wing alone, and the best location for tail. So where we have to keep the tail, the location for the tail when you are designing the aircraft, and which portion if you are going to position yeah, your tail, and where the wake formation will be less and the stability will be good. You have to check. And you can see here this is called cruciform, and we have a H tail, and we have a triple tail, and we have a V tail, correct? And we have a rudder waiters. Already I told you what are these rudder waiters, rudder and elevator. It is, you can see here this is called rudder waiters. You can see here the V tails are reduced interference torque, but at the same penalty in the control actuation complexity, as the rudder and elevator controls input must be blended in a mixture. So that is called and provide the proper movement. It is a V tail. They're called as a rudder waiters. Rudder plus elevators together called rudder waiter. They're called as a rudder waiters. Clear? And also you can see here this one we have to understand. It is called adverse roll yaw coupling. We will call. What is this adverse roll coupling? So it's a roll yaw coupling. The rudder waiters are produce a rolling moment towards the left in position, opposition to the desired direction of the turn, and an action called adverse roll yaw. So it's nothing but a what? Rudder. It is action of the rudder is yawing moment, and elevators will be the pitch up and pitch down. So therefore here what it leads, the pitch up and pitch down, it may leads to the yawing of the motion as well as a row yaw coupling. The coupling is nothing but a what, where the two and equal parallel force are acting and leads to the body to rotate. That will action will be done by a roll and yaw, that is by the rudder waiters. Rudder waiters also produces a rolling moment towards the left in position to the desired direction of turn and action called adverse roll coupling, we will call it. It's called. And also we have another concept called proverse roll yaw coupling, that is inverted tails. We can see that they are called as a, they are they are vertical and horizontal tails. They're called rudder waiters. We're called V tail. We will call our inverse of the V tail. That's called inverted V tails. You can see the position of it that leads to the Provost roll yaw coupling. What is this Provost roll yaw coupling? The inverted tail avoids this problem, produce a desirable Provost roll yaw coupling. This tail arrangement can cause difficulties in providing adequate ground clearance. So sometimes it may hit to the ground during the takeoff. So therefore, it should have a tail volume coefficient, and also this will, for the ground clearance, it will be a problem. And white tail, we can see this is called as a white tail. This is called white tail, and this is called boom mounted here. And we have a this is called, you can see, circular ring tail. It is just for a conceptual, it's a hypothetical one. Still we are not used this, and I can do a lot of research on the wing tail configurations and where you can stability part of the aircraft can be improved here. So we can look here, and we can see here these are called as a conventional type of tail, and we can see that this is called the twin tail and flying chase of the aircraft, mainly supersonic aircraft like F-22 Raptor. And we can see a tail arrangement of a spin recovery. So we have to understand here, you can see the aircraft, it is in the stall and it starts to spin. So it's called the incipient spin, lasts about 4 to 6 seconds in the light aircraft. So around 4 to 6 seconds will be there. This is for a lighter aircraft, micro light aircrafts. Approximately 2 turns will be there. You can see this is called approximately 2 turns. And fully developed spin, airspeed, vertical rotation, and stabilized small training aircraft loses approximately around 500 feet per second per each 3-second turn. So for each 3 second there will be a one turn will be there. And wing recovery, wing regain lift, and training aircraft usually recovers about 1/4 to 1/2 of a turn, or it is called anti-spin inputs, and again it will come back to the stable state. You can call spin, we will call. And this is called, you can see that there is an effect, and we have a less stalled and we have a more stall, and in which it is going to the like in which direction it's going to spin. You can see that effect of the tail arrangement upon the rudder control at high angle of attack. At high angle of attack, the horizontal tail is stalled. In the high angle of attack, there will be a horizontal tail is stalled and producing a turbulent wake extending upward approximately 45 degree, about a 45 degree. You can look here, and you can look here, the vertical tail plays a key role in spin recovery. And also vertical tail, what is this vertical tail? Functionality of the vertical tail is, for it is where the rudder will be there for the yawing of the aircraft, correct? So therefore yaw and side slip angle, we will tell. What is yaw angle is nothing but a what? We have a xi is a yawing angle, and beta is called as a side slip angle. So yaw and side slip are in they are in opposite direction, but the magnitude will be same. For example, if the yaw are given 5 degree, that is, the beta will be minus 5 degree, means they will be having the same magnitude but opposite in direction. So therefore the negative sign represents what? Opposite in direction. So therefore side slip as well as yaw angle. So therefore an aircraft is in a spin is essentially falling vertically and rotating about vertical axis with a inside wing fully stalled. The aircraft is also typically at a large side slip angle. It's called typically at a large side slip angle, that's called beta. To recover from the spin recovers requires that a wing will be unstalled and the angle of attack must be reduced. And however, the rotation must be stooped and the side slip angle reduced, or the aircraft will immediately enter the another spin. This requires adequate rudder control. So therefore, to have an adequate rudder control should be there. Otherwise, spin leads to the short pitch pole action, and it may leads to the crash also. We have two types of dynamic stability. We will call such type of things are called the dynamic stability. We have two types of dynamic stabilities. One is having a short pitch mode, another one is a long pitch mode, that is called fluid motion. So it leads to the continuous motion of the up and down. We can look into it, the spin when it enters to the spin. When we don't have a control, it may leads to the crash. So therefore you should be having a very careful in this such type of actions, and it's mainly controlled by the rudders, or it may be the vertical tail. Here this is called rudder lies entirely within the wake of the horizontal tail. You can see within the wake of the horizontal tail, and the effect of the wing, this is called unblanketed portion, where the effect of the moving the horizontal tail forward with respect to the vertical tail, and moving of the horizontal tail aft with respect to the vertical tail. We can see this dorsal fin, why it is. To avoid this, we can see we are increasing the area of it. By increasing the area, what we are doing, there will be a smooth flow. By increasing by a smooth flow, what happens, there will not be a wake formation. To avoid the wake formation, this dorsal fin we are giving up. To increasing the area, what we are doing, we are delaying the flow separation. We have to understand why the dorsal fin will be there. To to avoid the flow separation. By avoiding the flow separation, turbulency will be reduced. By turbulency, when it reduced, your stability will be good. So therefore, to avoid that, we are going to look at a dorsal fin, and also we have a ventral fin also. Okay, and the use of the dorsal fin improves the tail effectiveness at high angles of side slip by creating the vertex that attaches to the vertical tail. This tends to prevent the high angles of side slip seen in the spins. The arguments rudder control in the spin. The ventral tail is also tends to prevent the high side slip and has the extra advantages of being where it cannot be blanketed by the wing wake. So therefore, ventral tail is also used to avoid the lateral instability in high speed flight. Okay, so these are all called, you can see are looking into that moving horizontal tail upward and the T-tail arrangement. We have a different tail arrangement. We can see the flow over it. We can see blanketed and unblanketed and how it is affecting to the stability of the aircraft. And we can see a tail geometry. The surface of the areas required for all types of tails are directly proportional to the aircraft's wings area. So the tail areas cannot be selected until the initial estimate of the aircraft takeoff cross weight has been made. So therefore, one lesser until what is this takeoff cross weight? That is W naught is equal to we have a fuel weight, we have a empty weight, crew weight, and a payload weight. Correct. Once if we do that, we'll understand that what should be the weight of the each components. Clear. So initial estimation of tail area is made using the, please you have to understand this is called tail volume coefficient. We'll call tail volume coefficient method. So that's the initial estimation of the tail area is done by tail volume coefficient. Okay. And other geometric parameters of tails can be selected. We have a tail aspect ratio, and taper ratio shows the little variation over a wide range of aircrafts. You can see that this is called an aspect ratio. It's called a taper ratio for a horizontal tail. For a fighter aircraft, it should be 3 to 4, and sailplane will be 6 to 10. And we have a 3 to 5, and we have a lambda is 0.2 to 0.4, 0.3 to 0.5, 0.3 to 0.6, and we have aspect ratio 0.6 to 1.4, 1.5 to 2, 1.3 to 2, and 0.7 to 1.2. And we can see lambda is called taper ratio. So for general aviation aircraft use untapered horizontal tails, that is called mainly lambda is equal to 1. Okay, so we can look here. For low-speed aircraft, the horizontal tail sweep is frequently said to provide a straight hinge line for the elevator, which usually has the left and right sides connected to reduce flutter tendencies. Okay, so and also vertical tail sweep varies between 35 degree to 55 degree, and we have to look here. And also for high-speed aircraft, vertical tail sweep is used primarily to ensure the tail's critical Mach number. Understood? So therefore, the exact plane form of tail surface is actually not very critical in the early stages of the design process. The tail geometries are revised during the later analytical and internal studies. For conceptual design, it's usually acceptable to draw a tail surface that look right based upon prior experiences and similar design. So therefore, so whenever you are designing the one type of aircraft, when we look into a comparative study, so what type of tail we used according to that, by that previous experience, we are going to select it. We can do such like this, and also we can go accordingly. So we can see the different type of wings, and we can see here. Understood? So therefore, Airbus 300, 787 Dreamliner, and Airbus 380, correct? And you can see here they are called different types of ailerons. You can see that this is called wingtip. I'm speaking about wingtips. So this is called wingtips, we'll call, and this is called the low speed ailerons, and we have a high speed ailerons, and we have a different type of ailerons, and we have a slats, leading edge slats and trailing edge slats, and the spoilers, flag track, fairing. So these are the different parts of the wing. Understood? So therefore, we can look here, and we have Kruger flaps, we have a low speed aileron, three slotted outer fit, and spoilers. Clear? So these are all things when you look here. And so we can see a different type of flaps. Already I discussed about it. So by the flap, what is happening? By we are increasing the area and separating the, like we're delaying the flow separation. By delaying the flow separation, we are getting a good lift. So therefore, by lift is more, therefore they are called as a flaps, are used as a high lifting devices. And we have a different type of flaps here. And you can see plane flap. And during the World War I, what we used, mainly the plane flaps in the previous, in initial stages of the aircraft, what they're used. And we can see here Zap flap, and we have Kruger flap, and we have a Gurney flap, and these are called different types of flaps. We have to understand what is the function of the flap is mainly for high lifting devices. We can see a nose of F-22 and F-35. We can see nose, we can see 47.5 Mach, it is 1.3756. By reducing the noke, and you can see nose. So if it is a nose angle of the degree, it is more, You can see here it is more. If it is more, you can see that it will be lesser, that drag will be higher and it cannot go to the higher speeds. So therefore, if it is at a sharp edge, you can see that is a sharp edge. By sharp edge, we can have a 27.25-degree nose angle. By the wingtip angles, we can go from 2.184. You can see the speed of the aircraft, how it changes by F-22 versus F-35. Okay, and we can see a 90-degree, and we have a tail units. We can see here say all flying rudder, top flowing. We can see how it flows. Understood. And we have, can see a rear fuselage and the relative wind, and we can see there will be a separation, and to delay the flow separation, when we have this surface, it will delay the flow separation. By delaying the flow separation, it gives the good lift. Okay, so therefore, so these are all our different understood different types of tails, and we have a standard tail and twin tail. Clear? So please, we have to understand that is a this is called a standard tail. We have a fin and vertical stabilizer, and we have a twin tail. Clear? So these are the different types of aircraft, and also we can see that the portion of it, and F-22 versus nose to wingtip angles. So this is called wingtip and nose to wingtip. This nose to wingtip angle is 27 point. This angle I'm speaking about it. This angle it is 27.4, and this angle it is around 7.5. Then it's according to that. If it is more the wingtip to nose angle, so the if it is lesser the wing nose to wingtip angle, higher the speed. If it is a higher the nose to tip angle, the and we'll be having a lesser the speed. So we have to understand how the concepts of it, being a design engineers, then only we can understand how the aircraft can be designed. You can see here, so we can see here, this is the angle when I'm looking at it. It's a 55-degree from this ear to this. You can see here. So Mach numbers indicate the speed at which the aircraft wing runs into the nose shock. So therefore, front, when it runs into the shock front generated by the wing itself, you can see here. So you can see they're called a shock. So there will booms will be formed. You can see that when it is going at a higher speed and more than the speed of sound, and we can see they're called, you can see as a 90-degree, because this is the portion where it is a 90-degree. We can see that forms booms, how they are forming. Understood? So therefore, these are all things should be known. And we have this is a 30-degree. It depends upon the angle to the nose angle to the wingtip. According to that, we can tell that what type of aircraft it is and what is the speed of the aircraft. Yeah. So if you have any doubts, let me know.
Hello.
Yeah.
Sir, we'll be having